Good. Hi guys, welcome, good evening. Thanks for coming along to August's talk for Introduction to Astronomy. So, nothing beats a dark night. You know, this might be some of you. I'm not a boatie, but I know boaties enjoy this. They pop in a nice moonless night to a nice bay, no wind, sheltered for the night, and enjoy the night sky. It might be you camping. It might be Christine and Sid in their nice garden on a moonless night. But you know, you just can't beat a dark night. It's just absolutely beautiful. And you're probably familiar with some of the summer sky. We see here sort of little patterns in the sky, like everyone knows the pot and the handle and stuff. Moving on to the winter sky, and you probably which you can see in the sky at the moment, you can see the scorpion here with Antares, the heart of the scorpion. You're probably all familiar with the 2 pointers and the Southern Cross. But how many times do you look up the sky and you think, I recognise that, oh, isn't that beautiful? And you've got someone beside you that will be really neat, or even thinking yourself, what actually is that? Can I see any galaxies up there? That bright star up there, is that a planet or a star? What could it be? Why is that star red and that star sort of a white colour? You know, how many people often think that when you're looking up at the beautiful, beautiful sky? I know I have on many occasions. And that's why tonight's talk is entitled The Night Sky. What are we looking at? So the aim of the talk is for you to learn what is up there, what you are looking at, but more importantly, not knowing what you're looking at, but more importantly, knowing why and how you know what you're looking at. So when you do say to your friend, if you've got any friends left, when you do say, I know what that is up there, they can say, well, how do you know that? I'll tell you. And if you've still got a friend after that, good luck to you. But that's what we're talking about tonight. So the focus of the talk is going to be orientated around mainly with your naked eye, sitting on the deck of your boat, sitting outside your camp tent. There's 3 objects that I've put in that you can see with a good pair of binoculars, which usually people have got good access to. But that's what we're focusing on. There'll be some question time at the end of it. Having said that, if you've got any pressing question about a specific slide at the time, just hang out. Yep, and you all sort of got some handouts there, so they've all gone round, so that's good. Let's get started. So I've broken it into these chapters, or 2 parts, the big stuff and the smaller stuff. The big stuff, we'll look at the constellations, and then we'll have a look at the 4 galaxies you can see with your naked eye. And then we'll talk about the moon and the planets, and then we'll talk about the 2,500 large stars of the Milky Way that you can see, and then we'll sum up. I always like to sum up with 3 sticky messages that you can take home. Okay, so let's get moving. So in the 88 Constellations chapter, we're going to introduce the concept of the ecliptic plane and the changing night sky. You might be wondering, why does you showed me the summer sky, and then 6 months later we see a different sky. What's going on there? Why does the sky change from season to season? I'll show you how our latitude alters how you look at the sky, and then just briefly how to find south. Now, so constellations, the bottom line is the constellations are just regions in the sky, patches in the sky, and the importance of that is all about communication. I saw something bright in the sky the other day. You want to tell someone, well, what part of the sky, what region did you see it in? You can tell them the constellation. So there's 88 of them. So I thought if we spoke for 10, 15 minutes on each one, we should be out of here by the time the sun comes up, but we'll see how we go. They're defined by patterns or pictures. A lot of them are mythical stories and figureheads and so on that have been dreamt up over hundreds of years ago. The important thing is to say is these patterns in the sky are 2-dimensional. They're not 3-dimensional. In other words, if you might find that these stars here find a nice little pattern here, or you get a star, you've got the triangle. Those 3 stars aren't all the same distance from us, from Earth. The star might be here, this star up here may be way over there, and this star may be yay far away. So it has nothing to do with how far away the stars are. It's purely 2-dimensional, how we perceive them from Earth. So let's just look at the southern summer sky. So here is your pot. You've probably heard everyone call this here Orion's Belt, and that's Orion's sword. And you think, why that? The reason is everything is upside down the southern hemisphere, because a lot of these asterisms and pictures and so on were all created in the northern hemisphere. So, but also, just to give you an idea of what's going on here, let's put some lines in place, and you're starting to see all your constellations, and you still think, well, everything's upside down. Still a bit confusing, so let's put it up the right way. And here's some of your story. Here is Orion the Hunter. He's got a sword here. He's raising a weapon here. He's about to attack the bull, Taurus. You can see the horns, the two horns coming up here of these stars. Aldebaran in Arabic is eye of the bull. So he's fighting the bull. What does every good hunter have by his side? His best friends, the two dogs. There's Canis Major, there's Sirius, the brightest star in the sky, second to the sun, also known as the dog star. So that's sitting here, and there's Canis Minor, the second dog. Unicorn figure here, and so on. But a lot of the constellations are all together and make up a mythical story behind them. So it's a lot easier when you see the whole thing tipped upside down. The winter sky, I've showed you that picture before. So let's put some pictures in here. Here you go, here's the Scorpio, so you can see the tail down here. The Southern Cross, there's the cross, and the two pointers are part of the constellation Centaurus, which of course is a mythical figure, half human and half horse. So that's just a little bit about that. Now, the next question you might ask, hey, why does the sky and the constellation change during the year? And for that, we're going to introduce the concept of zodiac constellations. I remember for years I used to wonder, what are these zodiac constellations? What are they all about? All it refers to, these is that, well, from our perspective, as you know, the Earth orbits around the sun, but from our perspective, the sun traces out a path across the sky. And that path which the sun traces across the sky is known as the ecliptic, also as the zodiac path. And the constellations that also travel through that ecliptic path are collectively known as the zodiac constellations. And this just gives you a good idea why the sky changes. So here's the sun, here's the Earth orbiting. Let's go to wintertime where we are now. If we look this way, we're going to see the glare of the sun. We can't see anything. But at night time, we look that way, and there's the Sagittarius. If you were at the equator, that would be directly overhead. And month by month, we start seeing Capricornus, Aquarius, Pisces, and Aries, and Taurus, and we get round to Gemini in summertime. And so on, it goes around. So those are the constellations that are directly above you at midnight, also that travelling through that ecliptic path if you were at the equator. So that's all the 12 zodiac constellations mean, just collectively those group of constellations that lie on the ecliptic path. Now, we've done that, so let's move on from there. So, but of course, we are at a latitude of 36 degrees. As mentioned, those constellations lie directly overhead, what we call the zenith, or the path directly overhead, if you're at the equator. But of course, little old New Zealand, there's the equator there, we're 36 degrees south. And what that does is shifts things. So if you're at the equator, you look directly above, and there's your sort of where your zodiac constellations travel across, that's directly overhead, and at midnight the sun will be directly on the other side of you. If you look south, you'll see a point on the horizon, and it's called the South Celestial Pole, and the whole sky appears to rotate around that point on the horizon. But little old New Zealand, we hop in our boat and we start travelling down to 36 degrees south, and as we do so that straight up ahead, out to the South Celestial Pole, just slowly starts tipping, tipping, and tipping, and tipping, till you're 36 degrees. So that from directly above you to down there is 36 degrees, and of course your South Celestial Pole moves up 36 degrees. And all the stars that rotate around there are called, which I'll bring them up here for you, are called circumpolar. Here we go. So here's the zodiac constellations. Overhead, and they're a little bit north from us, so everything goes north and everything lifts up because we're going south. And yeah, oops, sorry. Yep. And these ones here, objects circling within 36 degrees of the South Celestial Pole to us, because we're latitude at 36 degrees, never set below the horizon. They're called circumpolar objects. And here's your South Celestial Pole sitting here, and some examples is the Southern Cross, the pointers. Achernar is a popular star that a lot of people know about. Those are the three big items that never set. They never go below the horizon, and of course you don't have to wait for their rise again. For us in Auckland at latitude of 36 degrees. So that's what's happening. So the South Celestial Pole and the zodiac path or ecliptic plane is all being tipped a little bit north, 36 degrees. How to find south? Straightforward. Of course, in the northern hemisphere, they've got the North Star, which is easy to point. We don't have that down here. We don't need it because we're far more intelligent in the southern hemisphere, the Americans and the English. So you draw a line through the longitudinal axis of the Southern Cross. You go to the midway point between the pointers and draw a line perpendicular, and where they meet, that's roughly the south celestial pole. If you want to know where south is, you just draw a line directly down to the horizon. So that's finding south. So that's the constellations. So you've learnt there's 88 of them. They're two-dimensional patterns, coincidental, nothing to do with distance. You know, the ecliptic plane is the plane at which the sun appears to move across the sky. Our latitude in Auckland, 36 degrees, alters everything, and you know how to find south. So this looks at galaxies. There's 4 galaxies. 3 main types of galaxies there are. I'll briefly show you that. Then we'll look at the galaxies we can see and where we lie in the Milky Way. So what is a galaxy? The bottom line is a galaxy is a gravitationally bound collection of gas and dust, stars, and typically billions of stars that are all gravitationally bound together. They're not likely anytime soon to start wandering off. And that's essentially what it is. This is a Hubble Space Telescope image. Every little object you see in here is an entire galaxy full of billions of stars. Pretty mind-blowing. So the 3 main types of galaxies, there's loads of subtypes. Don't get confused by them. The 3 types, spiral, as it here looks like something like a Catherine wheel or something here, and looking side on it looks like a disk. An elliptical galaxy, and the closest thing you could describe elliptical galaxy to would be like a rugby ball, the way it's shaped. And then, of course, you get galaxies with no particular pattern called irregular galaxies. So, yeah, there's 4 galaxies. Any takers that you can see with the unaided eye? Takers? Andromeda, yep. Yep. And Milky Way. That's another galaxy, yeah. You'd need a telescope to see the triangular, but yeah, we'll see the triangular in a minute. Absolutely, it's another spiral galaxy. They're never in the local group. So this is the Milky Way. It's a spiral galaxy. It's across from here to here is 100,000 light years. And you might say, what's a light year? A light year is the distance light travels in a year. And light travels at 300,000 kilometers per second. In other words, a blink of an eyelid, it can go around the Earth about 7 times. And you let light loose for a year, it travels for about 10 million kilometers. And that's 1 light year. And the galaxy is 100,000 of those across, because of light travels so fast. Almost as fast as my cat heads for the food bowl at dinner time. Now, where are we? So like all good galaxies, we've got a bar in the center, sitting there if you get thirsty. We sit out here about 26,000 light years from the center. So we're halfway out in the suburbs, and that's where we sit. Total number of stars in this Milky Way, estimates vary from 100 to 400 billion stars. A lot of people just settle on roughly about 200 billion stars. So just to give you an idea, you're talking in the hundreds of billions of stars in the Milky Way. So here we are. So there's the sun and the Earth going around it once a year, every 365 days, and rotating every 24 hours as it does so. So if we sit here, you might say, well, where are we looking? So in the lettered void seasons, June, July, August, i.e. southern hemisphere's winter, northern hemisphere's summer, during the night time, you're looking back towards the centre of the Milky Way. So you start to see its big bulge, which we'll have a look at it. So you're looking that way in winter time. And also just a note is the solar system is just slightly above the sort of level mid-plane thickness of the Milky Way. So the southern hemisphere, we have a more looking down view on the Milky Way than they do on the northern hemisphere. That's why all the northern hemisphere guys get quite excited when they come out here. There's a lot of stuff you can see out here you can't see up north. As the year goes by and the Earth goes around the sun like that, and you get down to winter time, and of course at night time you're looking back out this time. So our summer, North America's winter, you're looking out this part here, and there's the Orion Belt. You'll know Orion the Hunter with the pot and so on. So that's where we sit in the galaxy. That's what we're looking at different times of the year. That's what a galaxy looks like side on. It's got the disc here, nice sort of, there's a thin and a thick disc. Don't get too bogged down with that at the moment, but here's a bright, bulge, dense, glowing bulb here in the middle, and that corresponds here of the Milky Way, and that's what we're looking back at our winter time, about in the middle of the year. We're looking back that way. And there's some little globular clusters, but that's another talk. Now, a commonly asked question, people say, well, you know, everything moves and rotates. Absolutely, nothing sits still in the universe, particularly my cat, dinner time. And we also are rotating around the Milky Way. And our solar system goes around the Milky Way at 230 kilometres per second. So we're travelling around. The next people say, well, how long does it take to do a complete circuit of the galaxy? About 230 million years. So when we were last here, the dinosaurs were roaming around. And another question people sometimes ask, how fast does the Earth go around the Sun? It's about 30 kilometres per second. So you're talking high velocities, you know, we're talking blinks of eyelids. You know, the Earth travels 30 kilometres in the blink of an eyelid, and you're talking 230 kilometres with the blink of an eyelid here for the whole galaxy, for the whole solar system going around the Milky Way. So here's a nice picture, Southern Hemisphere winter view. So what you're seeing here across, what are you looking at when you're seeing this lovely big strip along here? It's known as the Milky Way, because it just looks a big blur to a degree. And it was Galileo, with his the first guy to take a telescope and look up into the skies. And he had the insight to realise the Milky Way, which means spilt milk, because it looked like a big spill of milk, was actually, you're looking at billions of stars so distant we can't resolve them with our eyes. And that's why it just looks like a big milky blur. Here's that bright, dense central bulge again, looking back here. So that's the bulge that we're looking back at. That's it here. And you might say, well, all these big dark, dusty big lanes and things going through here. That is, yeah, dense clouds of gas, in particular dust. You know, they're not very big dust particles, but there's just zillions and zillions and zillions of them out there that make up throughout the plane of the Milky Way, and they get in between us and the stars behind them, and they create those big dark patches there. So that's what you're looking at. That's where future stars will be formed in those regions. So that's when you're looking at the Milky Way, that's what you're looking at. You're looking at the disk side on. You're looking through there or through here towards that way. And that's what you're looking at when you're looking at the Milky Way. And essentially it's just billions of stars so distant our eyes can't resolve them. So the Andromeda Galaxy, yep, Andrew mentioned. So the Andromeda Galaxy, so there's three main galaxies in our what we call local group. It's a little sort of galaxy cluster, consists of about 80 galaxies that they're aware of. There's three big ones, the Milky Way, Andromeda, and as Neville pointed out, the Triangulum. The Andromeda one, which is our closest large galaxy, is 2.5 million light years away. It's the furthest object you can see with the unaided eye from Earth, and that's it there. What you're looking at with the unaided eye is a little that little smudge is actually the central dense nuclear bulge of the Andromeda Galaxy. So what you're looking at, say that's our Milky Way one, that's the Andromeda one. I did a talk last year online that showed a series of pictures in the sky, what it would be if the Andromeda Galaxy, if you could see more of it, and it just takes up a large chunk of the sky. It's about 140 times the size of the Milky Way, 40% larger.
Is that a photograph taken July 29th?
Yes, so what I've done, good question. A lot, when you see dates up here, these little shots here, I've just taken them off Stellarium. And knowing I was giving the talk around here, you'd probably want to know, is this visible this time of year and when can you see it? So well pointed out, thank you for that. So you'll see little dates and times up here. So I got the Stellarium program and just typed in, found the object I wanted and made a note of the date and time when you would see this exact image. It's very low on the northern horizon. It's really a northern hemisphere object, but you can see it low down on the northern horizon from Auckland. So that's Andromeda Galaxy. So that's your second galaxy you can see.
Oh, could I just interrupt? If you're looking for it, the Great Square of Pegasus above it is a really good marker to find it. It really is easy to see to the north, and you can figure out where it is as soon as you spot the Pegasus. It's very low though, so you need a clear northern horizon. I've seen it at Andrew's place from the tour day, but I don't see it at home because we've got a blocked northern horizon.
Yeah, so that's the second galaxy you can see. Another one, here's a picture of a more obviously advanced telescope, nice picture here, photograph of the Andromeda Galaxy. What do you notice about these? What are these two things here? They're satellite galaxies. Yes, small little galaxies that hover around the Andromeda Galaxy. And the Andromeda Galaxy is not the only one. We're not going to go without any as well. So we have two, we've got a few satellite galaxies, but the main two that you can see with your unaided eye is the large and the small Magellanic Clouds. They appear as little faint cloud-like wisps in the southern summer sky. You would be mistaken for saying, oh, there's a little cloud. How did that patch of cloud get up there? But the rest of the sky looks good. Have a closer look. Even get your binoculars out there. It's just full of billions of stars. These are actual galaxies. Small galaxies, relatively small galaxies, but still reasonable size, 30 billion stars in the large Magellanic Cloud and about 6.5 billion in the small. That's about 160,000 light years away, and you're talking 200,000 years away for the small Magellanic Cloud. That is a decent size, whereby it's even got a bar down the middle of it, the large Magellanic Cloud. Up till recently, they've thought that these are two galaxies that we've captured some time ago, and they're in the process of going round and round and slowly merging with the Milky Way. The current evidence suggests that they're actually just approached the Milky Way, and this is their first turn into the Milky Way. Of course, with eventually to merge. I should mention Andromeda is going to merge with us in 5 billion years' time. Winston Peters will still be on a soapbox. They'll still be talking about Penlink and stuff. But yeah, 5 billion years' time, and we will merge with Andromeda. So there's really the 4 galaxies that you can see. How to find them? They are so faint they don't really show up in the stellarium here, but I thought I'd put it here for you to see the location. And the best way is you find the south celestial pole. So draw your line here. So your south celestial pole's about here, then go straight up. And if you do look for them and you know you're in the right spot, you will see them. But it's if you just go up there, oh, where are they? Where are they? You might struggle to see them. Once again, I put the date and time here. This is 10 p.m., 1st of February, to give you an idea of the summertime. The small Magellanic Cloud, it's smaller, and you just go simply, it's lower to the horizon, a little bit west. So you find your large Magellanic Cloud, go down a little bit and further up to the west, and there's your small Magellanic Cloud. So they're both there in view. If you know where to look for them, you'll see them.
Is it, say, central Auckland, is it possible with the naked eye, with the light pollution at 10 o'clock at night?
I'm at Gulf Harbour and I see them. I couldn't say if anyone was back to his backyards.
No, because of the LEDs.
Yeah, okay.
I've seen it on the shore.
Yep, there you go, yeah. Because I'm just in Wangaparaoa and I see them very clearly. Once again, only if you're looking for them, yeah.
The shore you can see them.
Okay, yep.
From our place.
Yeah, yeah.
I don't know if we can now, can we, Bill?
Depends whether they're, in the winter they're quite low,
Yeah.
and the right in the really bad sky glow. So it is better in the, that's slightly different time of year. You can see here February, but the small and large clouds are sort of the highest point at different times of year. So you want they're easiest to see when they're higher in the sky.
Right.
Okay, so the 4 big galaxies that we can see, the Milky Way, the Andromeda, and the large and small Magellanic Cloud. So if you know what you're looking for out there, you can say to someone, you can see 4 galaxies just with the unaided eye. Now let's talk about the smaller stuff. In particular, we'll start with the solar system, the moon and 5 planets, and you'll see how the sun is a star, generates its own light, and then the moon and the planets reflect the sun's light, giving rise to the moon phases. And also you'll see how all of this relates whereby the planets look different to the stars. You can actually separate them and you'll know how. So let's just touch upon the moon briefly. Most of you probably know this, but I think it's important to mention it. So you've got the sun in the middle of the solar system. That rotates on average every 27 days. It's a whole different talk. But you've got the Earth rotating, or orbiting rather, around the sun every 365 days. And then you've got the moon rotates every 28 days, and it takes about 28 days to go around the moon. The eye, because a lot of people say, why the phases of the moon? Why does the moon change? And the bottom line is, with the moon, is the key to it is at any one time, half the Earth is illuminated, but at any one time, half the moon is illuminated and half is not illuminated. And it's that straightforward. Let's start what everyone knows, the full moon. So here's your sun, here is the Earth, midnight looking away from the sun, and at noon looking towards the sun directly. Here is the full moon, and the bottom line here is you can see the full illuminated half of the moon is visible to the Earth, and we see that. And everything that we can't see is dark. As the moon orbits around, you get round, for example, to what they call last quarter, and once again, half the moon is illuminated, but because of the angle we're looking at the moon, we're only seeing half of that half. So we just see a quarter of a moon that's been illuminated. As the moon goes round, once again, half of it is always illuminated, but that full half is directed towards the sun, and of course we don't see anything because we're looking at the dark half, so we call it a new moon. We don't see the moon sitting there. And it goes around and the same happens again. Half the moon is fully illuminated, but we only see half of that half. So that's sort of, in a nutshell, what's going on with lunar phases. Occasionally that gets asked at dark sky nights and so on. Now let's get into some fun and have a look at the sun and the planets. As I mentioned, the sun is a star. It generates its own light, and then that light is reflected off the planets, and that's why we see the planets. I just thought I'd throw this in here to give you a perspective of the size of the sun. I think it's about the diameter. Here's Jupiter, Saturn, Uranus, Neptune, there's Mercury, Mars, and there's Venus and Earth. And the diameter of Earth, I think you can fit across the diameter of the sun 330,000 times to give you an idea of the comparison of the sizes. It's all about the sun, the solar system. People often say, is it always stars, planets floating around stars? And a good answer to that is, have you tried baking a cake without spilling some crumbs on the bench? Next to impossible. And it's all about the cake, the sun. And the planets are just leftover debris in what we call a circumstellar disk, which was another talk. So how do you know it's a planet reflecting light when you look up in the sky and you see something? And there's 4 key features that gives you the clues that you're looking at a planet, not a star. Okay, so just first of all, the planets are generally brighter and larger. You think, well, you've just told me that these things are really, really small compared with the sun, and the sun's just another star. Stars are far huger. The bottom line is the planets are a lot closer. So naturally, they're a lot bigger. Their apparent size in the sky is much larger than the stars, significantly larger, what we call the angular size. They're brighter because they're closer to the source, which is the sun of the light. So the whole point is that reflected light coming to us, it's coming out to us from a shorter distance. The other thing is to consider is planets, the distance to planets is measured in kilometres. The distance to stars is measured in light years. That is a good putting in perspective. The stars are just so far away from us compared with the planets. So the planets naturally are going to be brighter and they're going to be larger. That's one point to separate them. The planets don't twinkle or flicker like stars do. And the logic behind that is, in our atmosphere we have little cells or little packets of turbulence, of air just turbulating, moving around, very small little packets of air with all turbulence in it. And the light beam or light path, if you will, of that light coming off a relatively large planet that we see in the sky, because it's a lot closer to us and a lot closer to the sun, that comes through, and the size of that light path is larger than the little pockets of turbulence when it hits through the atmosphere. So the light is less interfered with, and a lot of the light just carries on through uninterrupted. As opposed to the light from your stars, but the stars are so far away, numerous light years away, their little path or beam of light that comes through our atmosphere is significantly smaller than those little packets of turbulence, little cells of turbulence going on in our upper atmosphere. So at times light comes through, then a little bit gets reflected or scattered here, a little bit gets scattered here, a little bit gets through. So it gives us that flickering or twinkling effect. That's the reason why. Is the light beam coming to us from a planet, that light reflected from the sun, is larger than the ones from the stars and larger from the little packets of turbulence in the upper atmosphere of the Earth. Number 3 is the location, and we've all talked about now, as we talked about earlier on, the ecliptic plane, is that the sun follows that path across the sky. You'd say, for example, from Auckland, say, we see the sun somewhere in an arch across the sky, that ecliptic path. It might vary a little bit with season, but you don't see it suddenly over here and suddenly over here, suddenly over here. No, it follows that sort of broad path. And the planets do as well. They move across the sky within that same ecliptic plane. And you might say, well, why is that so? Well, the reason being is that the planets all orbit the sun in the same level plane. And it's all to do with when stars first form. You've got this rotating big mass of gas and dust. It's contracting down under gravity. It's starting to spin faster and faster and faster. What do you get when you start spinning something faster and faster? You start getting centrifugal forces sending a little disk out, numerous names for them, or protoplanetary disk. So all the stars form of that disk formed by centrifugal forces as that star has been formed. So that's called the ecliptics. That's why those are all in the ecliptic plane. They're all in the same level. So we see them go, from our perspective, see them go across our location in there. So, for example, if someone says, oh, what's that bright thing on the horizon over there north? And you go, well, it ain't a planet. But it's not twinkling and it's bright. It's not a planet. It's not in the location of a planet. Or if someone says, way over south, oh, could that be a planet? No. How do you know? You tell them how knowledgeable you are. Well, the planets go in the ecliptic plane, the path that the sun goes.
So, just looking at so the sun has its movement changes during that. You had it on that slide before.
Yes.
The solstices and the equinox.
Yes. Yep.
Similarly, Saturn and Jupiter present in the winter sky tonight, for example, will be tracking that the changing path that the sun takes throughout the season.
It gets a little complicated. It's the actually opposite because the plane is tilted, and in summertime the sun follows, for us, it follows sort of an arch like that, and the planets follow the arch as the sun went at wintertime, and vice versa. Yeah, because the plane's like that, and we're in, say, summertime. Meanwhile, the other hemisphere's in wintertime, so it goes at an angle. So it's similar principle. I didn't want to go into too much depth there and confuse people, but it's in the broad ecliptic plane. Yeah, but you're quite right. It is different from season to season.
And similarly, the zodiac then is in the broad ecliptic.
Yes, yep. Because the ecliptic does change with seasons. Absolutely. Yep. Are we all familiar with that? Why they have the seasons? A lot of people say, why do we have seasons? It's because the Earth sits at its axis is tilted at 23.5 degrees. So you might see the sun doing an arc here if we're in summer, but the planets are doing the arc across here at night time, and the Zodiac Constellations as well. But that's why we have seasons, is because of the tilt of the Earth. That's a whole talk, but it's a lot of fun.
Well, generally, Chris, I should just say Jupiter and Saturn are both close to opposition at the moment, so it's a nice time to actually observe them.
I'm going to show them that. That's the homework at the end of the talk. Yeah, yep. Okay, so...
Also, planets do twinkle if you have them low on the horizon.
They tend not to be from well, unless the setting and rising, because you've got more atmospheric disturbance. Yeah, and it's all to do with that, because people often say, oh, planets don't twinkle because that's reflected light from the sun, not self-generated. And I say, two right facts, but wrong reason linking them together. Sure, it's reflected light. Sure, they don't twinkle, but they don't twinkle because of turbulence in the sky. And as Neville's pointed out, you get further down on the horizon, you're looking through more atmosphere, and you can start getting a twinkle. But I'm trying to help people, in the middle of the sky, get some rules. So the fourth thing that planets have, that stars don't have, is they appear to wander inside that ecliptic plane. In fact, the word planet actually means wanderer. And you might say, really, why is that? And one of the reasons is that the planets travel across the sky a lot faster against the background stars. And the reason they do that, once again, they're closer. And it's like sitting in the park watching a dog run across the park, say 10 kilometres an hour, like that. Then you look in the distance and you see an aeroplane, a few kilometres up, and it's probably doing 600 kilometres an hour, but it's just doing that to you. Same principle. Stars are far away, they're travelling at high velocities, we just hardly see their movement at all, but because the planets are much closer to us, we see them move a lot faster. So the planets travel faster across the sky than the background stars, so they're not always matching up each year with the same background stars and the same constellations. So they're considered to wander. Yeah. The other thing is they also vary in relative speed to one another. It's not like you've got Mars here, Jupiter here, and Saturn, and they all race across the sky. They're all doing their own crazy things. And the reason behind that is it all comes down to the force of gravity causing planets in closer orbits to orbit the sun a lot faster than the planets as you go out. An example is the Earth once every Earth year. Mars, further out, takes 2 Earth years to go around. Jupiter takes about 12 Earth orbits to go around as you go out. So it's probably easier for me to point this out to you here. Here's Earth. So you go out a little bit. Mars takes 2 Earth years to go around. Jupiter takes about 12. Saturn takes about 30 Earth years to go around, because the orbit is all to do with the gravitational attraction. That's what's driving the orbits, is the gravitational attraction of the sun. So it makes sense, the further you're in, the faster you go. So that from our perspective too, the planets all move at different velocities to one another. And there's another interesting thing here, is sometimes the planets, from our perception, we see them to go backwards. And it's because our perception, if we're travelling at a faster velocity than, say, Mars is travelling around here, and as we go past it, Mars appears for a brief moment in time. Here's your dotting of the Mars. It appears to go backwards for a time. And that also, that's all just from our perception of it all, and is because of the different orbital speeds. We're travelling faster than Mars because we're closer in to the sun. So those are really your 4 main things. They're brighter, they're larger in the sky, they don't twinkle. You'll see them in the general region of the ecliptic plane, and you'll see that they don't match up with the background stars each season and each year and so on, because they're travelling a lot faster from our perspective. So let's look at some individual planets. Mercury and Venus, you'll always see them close to sunset or close to sunrise. They hug the sun. Why do they hug the sun? Because their orbits are closer to the sun. You know, they've got the sun, you've got Mercury, you've got Venus, then you've got Earth. So from our perspective, they're always going to appear closer to the sun. So they hug the sun. Mercury's reasonably faint because it's small. Venus is always very, very bright. There's a few reasons why. One is it's close to us. 2, it's relatively close to the sun. And the third one is it's got a global, thick, dense cloud cover around it. And clouds are wonderful at reflecting light. So there's 3 reasons why Venus is so bright. And for that reason, it's often known as the morning star in the east, if it's near sunrise. And if it's near sunset in the west, it's called the evening star. Here's Saturn up here. You can see, once again, all the planets are lined up, because they're not higgledy-piggledy all over the south. They're all over the sky. They're in that plane all the time. Here's a shot of, here's another one of Venus, once again near sunset. Here's Mars. Mars has a red sort of tone to it. Its soil is heavily oxidized, sort of like rust-like, and that gives it a red hue to it. Here's Saturn and Jupiter. This tells me immediately, if you're looking south, and you see the planets forming quite an arch looking south, this photo, you'll automatically go, okay, this was taken in the northern hemisphere. Well, I don't think it's actually a photo, it's a program, but it's taken from a view from the northern hemisphere, and probably down towards, more towards polar latitudes, because of the arch. Okay. Now, Jupiter, so you've got Jupiter and Saturn. Another thing to point out, Jupiter is a lot larger and brighter than Saturn. 2 reasons. One, it's a heck of a lot closer to the sun and to us than Saturn. And the second thing is it's the largest planet in the solar system. So Jupiter are the 2 big, Venus and Jupiter are the 2 big bright ones that you'll often see. Saturn has got a very faint yellow hue to it as well, sort of a yellowish brown colour, and that's due to hydrocarbons in its atmosphere and ammonia as well. And it gives it that sort of slightly brownish yellow tinge to it. Which your homework will be coming up shortly, and as Bill pointed out, they're in the eastern sky at the moment in the evenings. You can see them beautifully. Yeah.
So how many planets can you see with the naked eye?
5 planets. Yeah, 5 planets, which we'll go to. So you've got Mercury, Venus, Mars, Saturn, and Jupiter.
At the moment, you've got Mars and Venus sort of in Leo, which is in the western sky.
Yep.
And Jupiter and Saturn on the eastern sky.
Yep, absolutely. So we've got some lovely viewing at the moment. Yeah, yep.
So is that, say, Venus
Yeah, it's setting at the moment, west, yeah.
Yeah, will that happen will it be in that place sort of around this time, winter solstice, sort of in the evening over in that part of the sky?
Well, they tend to wander. Once again, the planets are wanderers. So you can't rely them on to be in exactly the same spot every year, same time every year. You'll always see Venus hugging the sun, because it'll always be in the western sky at sunset. When we can see it, there are other times at the other side of the sun. But when you can see it, it'll always be close to the sun.
Not necessarily
at the same time. Yeah, correct. Not necessarily at the same time each year.
summer and the evening.
Yeah, correct. Yep. Yep.
Of course, there is one other planet you can see all year round, all day long.
Yeah. Yeah, Earth.
This one.
Yeah, this one. So, yeah, out of the 8 planets, of course, we're on Earth, of course. You can see 5. And I've got a nice little mnemonic coming up with one of my sticky messages, how you remember all this. Jupiter and Saturn, this is 10 o'clock tonight. There you go. So there's your eastern boundary there, your horizon. There's Jupiter and there's Saturn directly above it. You can't miss them. They're out there. You'll go out later on or tomorrow night, the next cloudless night. They're in their full glory. They're beautiful. If you look through them with a good pair of binoculars, with Jupiter, you should be able to see the 4 moons, that middle, the tiny little dots. This is a little bit blown up, but to highlight the point to you. But if you've seen this, you'll know what you're looking for. I saw it with a pair of binoculars, 15 by 17 of Andrew's Astron's binoculars just the other night. Of course, the magnification, you've got to hold it against something, either a post or the side of the house or something like that. But yes, I saw some of the bands and I saw all 4 of the major moons. So that's, similar thing you can see with a good pair of binoculars. And now you know we're in the sky to find Jupiter. Saturn, again, that's pretty much what you see. There's the ring system. In a good night, you can see its largest moon, Titan. So it's good. Saturn is it's the lightest planet, where it's the only planet in the solar system with its density less than the density of water. So if you had a bathtub big enough, you could put it in it and Saturn would float. But of course, when you pull the plug, it'll leave a ring. Sorry, guys. That's beyond a dad joke, isn't it? That's a granddad joke. But that is true. True story. That's a true story, though. It is. It's lighter than water, its density. Here's Venus and Mars. This is on Stellarium. I'll get rid of the tree in a minute. I just kept the tree, and they have it make it look realistic, and it blots out Mars. And I'll get rid of that in a sec. But they just did that to show you how low on the horizon is. So that's 6:30 p.m. tonight, and probably tomorrow night, and so on and so on. Recent times. So you've got the big bright star to the northwest, Venus, the evening star, and you've got Mars. Let's get rid of that tree. And once again, Mars is that one there. It's just a background star, these ones here. But you can see Mars with the yellow hue. So assuming you don't have a tree in your backyard in that position, that's what you'll be able to see in the early evening.
The star is Vitalus.
What?
Alpha Leo.
Is it? Okay. I didn't know that. Alpha Leo. That's good to know. Thank you, Neville.
It is well past this time. Mars is very far away, so very small. So
Yeah.
wait for a year to let you see it.
Yep. So just what have we talked about? We've talked about roughly the 4 main lunar phases, and it's all got to do with at any one time, half the moon is illuminated and half not, and it all comes down to our perspective, what proportion of that half we see. The planets are larger and appear larger and brighter than stars. They also don't twinkle or flicker like stars do, and they wander in the ecliptic plane, so they're in that zone, and you see them wandering around throughout the year. So that's how you separate stars from planets from stars.
So stars are seasonal, aren't they? Certain seasons you're guaranteed to see certain stars.
Yes, they're fixed background stars, if you will. Why? Because the sheer distance to them.
Planets are in no way, not one of the planets that we can see is in any way seasonal. They come and go.
They come and go according to the orbits, our prospective orbits. No, yeah. Yep. So if you get a book, for example, the night sky, what's in the sky tonight, in the back of books and stuff, those charts, they're all, you think, oh, this is a couple of years old. That will be fine for the stars, but just don't rely on it for the planets.
Right.
Yeah.
Every year it changes.
Yep. Gets a little complicated too, the precession of the Earth, but 26,000 Milankovitch cycle as the tilt of the axis of the Earth changes, but let's forget about all of that. So that's, yeah, exactly. Okay, so there's roughly about 2,500 large stars that you can see in the Milky Way for the average eyesight on the average good, clear, dark night. Now, that varies hugely where you are, but that is the average. It's between 2,000 and 3,000. So I've called it 2,500 large stars that you can see. Stars generate their own light by nuclear fusion at their cores. Now, this is important. Stars evolve and change their appearance, and stars differ in their size and brightness. So I'm leading somewhere with this. Let's have a look just for a few minutes at stars. Stars are like us. They're born, they evolve, and then they die off. Stars always start their life and you get this huge, big, large molecular cloud full of gas and dust, many light years across. And it's sitting in a reasonable stable state. And suddenly a little bit of instability sneaks in. It might be a supernova explosion or maybe a bit of another passing large molecular cloud. But you start getting, the cloud starts rotating, spinning a little bit, and starts contracting in with gravity. But you get little knots or clumps of heavier density, and they start collapsing quicker and form into stars. So the bottom line is you get large molecular cloud, they often call them stellar nurseries, and from then you get groups or clusters of stars that all form at the same time astronomically, in astronomical times. They're all brothers and sisters, same constitutions, and what makes them up, the composition. Now, stars then, so then you get your stars, and we call this the main sequence. And this is where stars spend 90% of their life in a stable state, quietly fusing or burning hydrogen into helium, which generates energy, which of course makes the star shine, powers the star. So that's important. It's called the main sequence. 90% of their lifetime is here, and they're in a stable state. You then decide where they're going to go from there. As stars get older, they start to swell up. It's a topic of another story. But in a nutshell, the core runs out of hydrogen. So the star starts burning hydrogen in its outer layers around the core, and that causes the star to puff out and become red and very, very large and a little bit cooler. But that is another talk. So how do you classify them all? So they break stars down to solar masses. A solar mass just refers to the mass of the sun, which is roughly about 2 times 10 to the 30 kilograms, just 2 and a lot of zeros. So that's the mass of the sun. You've seen how big it is. But anything less than 8 times the mass of our sun is considered a small star, or a low to intermediate sort of mass. It swells up to become what they call a red giant, and then slowly with time, and this is only 10% of its lifetime it spends here, it suddenly becomes, its outer layers become more and more unstable as more nuclear fusion occurs in its outer layers, and the outer layers start to slowly puff out into these beautiful things. You've probably seen these images in books. They're called planetary nebula, but they expose the core of the sun, of the small star called a white dwarf. So all I'm going to mention here, because the talk's not about those. Main sequence stars, if you get a large star greater than 8 solar masses, it swells up even more and more and becomes a red supergiant. And I'm about to show you some pictures of comparison of their sizes. They eventually become unstable, their core collapses. Long story, but the bottom line is their core collapses. They then, the whole outer shells come down, collapse on the collapsed core, and rebound off into a big explosion called a supernova. As for the core, in a star that's between 8 and 20 solar masses, it ends up as a neutron star, and anything over a core greater, from a star greater than 20 solar masses, ends up as a black hole. So the main point of here is that stars swell up at the end of their life. The last 10% of their life, which is a small proportion, they start swelling up. And of course, what happens when something gets larger? It gets brighter and easier to see. That's one of the really key messages of tonight. So I've spoken a little bit about them, which we'll look at further. So let's take a step back, and let's just briefly look at these main sequence stars. So these are the stars that spend 90% of their lives here in a nice stable state. And they are classified into classes defined by their temperature, how hot their surface temperature is, and how bright they are. And it starts here at the little wee sort of small cool stars called M and K. You move up into G stars, and you go right up to A, B, and O. And you might think, when I went to school, the alphabet went something like A, B, C, D, E, F, G. What's all this about? And the bottom line is, it did go like that many years ago when they didn't understand stars fully, and they were classifying stars according to the amount of hydrogen lines they could see when they looked at the spectrum of the light of the star. But of course, they started understanding stars better. They kept the assigned letter with the relevant star, and so it looks, that's do they have. The mnemonic for it is, oh, be a fine girl or guy, kiss me. And then there's LT, another group of, below that again, and the LT is like this. So there's a little mnemonic to remember it, but you soon get used to it. So here's your red dwarfs, your K and M stars. Their surface temperatures on average is about 3,000 degrees Kelvin. These temperatures, you don't need to worry about Kelvin and centigrade. They're all the same roughly. Here's our sun here. Our sun's a G class. It's got a surface temperature of 5,800 degrees. Here's Sirius, the dog star that we looked at earlier on, the brightest star in the night sky. It's an A class and its surface temperature of about 10,000. You get up to these big O boys, hot, large and bright stars. They're getting up to 40,000 degrees Kelvin. So you might think, if I were to say to you, what's the commonest type of stars you see in the you see in the galaxy? The hands would bolt up if you didn't know any better, but I know you do know better, is you'd be saying, oh, these O stars, they're going to be the brightest and the hottest and the largest. We're going to see zillions of those babies. Hardly see these at all, but there's a catch. There's not equal numbers of all types that are made. And nature has a tendency to, when these big, large molecular clouds start collapsing down to form clusters of stars, far, far more. It's another topic of another whole talk about gene stability and gene lengths and so on. It's another whole talk. But the bottom line is, there's a huge tendency, the smaller the star, the more of them. And often people like to describe it like a pyramid, loads and loads of smaller stars. But you know what? It's not even a pyramid. The graph just goes like that, straight up. So your K and M stars are considered red dwarfs. They make up almost 90% of all the main sequence stars are these tiny little wee red dwarfs here. There's your G class that we live under. But look at the O class, 0.00003%, almost non-existent. They're very, very rare. Even the B class stars, less than 1%, roughly say 0.1%. But look how the numbers start climbing very quickly to the point of it's all top heavy. So let's move on from there. And so red dwarfs make up 90% of the main sequence stars, but the bottom line is they're so cool and they're so small and they're so dim, we can't see them with the unaided eye. The closest one to us is Proxima Centauri. You can't see that with the unaided eye. The Northern Hemisphere, same famous star called Barnard star. That's a red dwarf. You can't see that either, and that's one of I think that's the closest star in the Northern Hemisphere. So the red dwarfs, there's zillions of them, but we can't see them. And I'm talking about, in your campsite, on the deck of your boat, with your unaided eye, can't see them. You need a telescope to see them. So plenty of them, but forget about seeing them. What takes them out? The O and B classes, these ones here, hot, large and bright, as you said, you always thought plenty of them. They're too rare to see the numbers. You're talking 0.13% of the stars on the main sequence of these babies. There's not many of them. Plus, the big stars only live for short lengths of time before they go supernova. And I've got a nice little graph here. See, here's one solar mass. As you know, many of you know that the sun will spend about 12 billion years on the main sequence as a G star before it sort of extinguishes itself. We're about 5 billion years into it, so you've got plenty of time to get on with stuff, whatever you like to do. So that's here. But look, certainly you start to move up to these big O-class babies, you're talking 4 million years. So I got my calculator out. Yeah, the lifespan of our sun is 3,000 times longer than an average O-class star. So these babies, these big bright suckers, not only are they so far few in between, they only exist for an astronomical blink of an eyelid. So, and that's why you don't see them. So forget about the O's and B's, forget about the red dwarfs, the K and M's, if you're trying to find them. It's really these ones here, the G, F and the A class, that can be seen if they're close enough to Earth. And you tend to the classes, main sequence stars here, you tend to the ones that are visible to us from the unaided eye. As I mentioned, you measure stars in light years, you're talking in the tens of light years, like 10 or 20 or 4 or 30 light years. Not much more than that. You don't deal with the hundreds, which you'll see another group of stars, you see them for hundreds of light years. So we can see moderately bright, close G, F and A class. Forget about the O's and B's, forget about these guys. It's this group here that we can see if they're close enough to us. Now, going to the red giants, and I said I'd promised you, this is the slide I promised you, to give you an idea how big these babies get. Here's our sun here. Here's Sirius, the big thing in the sky. Look at the size of Betelgeuse and Antares, big supergiants. If you put Betelgeuse in the middle of the solar system, its surface would go out to the orbit of Jupiter. Antares, of course, much further, you're heading towards the orbit of Saturn there. So these babies, look, compared with the sun, these are huge. And what did I say about when you get large? You start to get a lot brighter and a lot easier to see in the sky, whereby 62% of the stars that we can see with our unaided eye are these big subgiants, giants, or supergiants, usually these guys here, in the latter stages of their life, and that's the key to it. What we can see in stars is predominantly late stage, unstable, huge giants and supergiants. 38% is closely, moderately bright main sequence stars. The others are not bright enough or they're too scarce to see. And I've got a little diagram here, a little histogram that Grant Christie sent me, but emailed on Thursday. And you'll see here's your main sequence stars making up roughly 38%. And here's all your white dwarfs, forget about those, 0.02. But look at these supergiants, giants, subgiants, and bright giants. They're all giant stars. So roughly 62% of when you're looking at the sky, you decided, nope, that's not a galaxy, that's not a planet, I think that's a star. More than likely, there's a better chance it's actually a late stage giant red giant in its latter stages of a star's life. It's less likely to be a main sequence star. So let's just have a look at some of the popular stars. We call things, anything bright in the sky, you call it stars. They're not all stars. So this is here, we have Orion. Here's the pot, here's the handle in the pot, or if the Northern Hemisphere people would say it's the sword. Can you tell what's the middle star?
M42.
Yeah, Neville's right onto it. Neville, absolutely spot on, M42. Remember we spoke about large molecular clouds. This is probably more of a telescope picture. You wouldn't see the red, but I just threw it up here. You will see something with binoculars. It looks like looking at fog or mist or haze. You will see that with binoculars. So I put these just to show you. That is a large molecular cloud that started collapsing down. It's the early stages of a star cluster where the big stars that burn up their fuel a lot quicker, they're up and running, they're blazing, they're emitting powerful ultraviolet light, which is causing all the hydrogen gas to fluoresce around it. And that's what you're looking at. So you won't see those colours with your binoculars or your telescope, but you will see it. It looks all fuzzy and cloudy. The word nebula means mist in Latin. Gorillas in the nebula. There's a movie for you. Okay, that's a bad joke, isn't it? Sorry. That's about 1,200 light years across and 14,000 light years away from us. So that tells you, look at these big objects, you can see them from much longer distances. Okay, so here's Sirius, the dog star. Let's have a look at that. That is one of your main sequence stars. It's an A class. It's one of the brighter of the ones that you can see. But look at its distance, 8.6 light years. So it's less than 10 light years, and that's why we can see it so clearly. Let's look at Aldebaran. Aldebaran, as mentioned, means eye of the bull. And there's your Taurus, the bull. There's its horns. With Orion, there's a shield and fighting him. So Aldebaran, that's a red giant. So notice 65 light years. We can still see it brightly because it's a red giant. It's a lot bigger. It's a lot brighter. So you're getting up into 65 light years. Betelgeuse. That's always been in the news. That sort of, is it going to go supernova? That's a red supergiant. We can see that at 640 light years away. Why? Because you saw the picture of how big it is. I think I did slip this one slide back in for you. That's why. Look at this. Look at the size of these guys on the main sequence, Sirius and the Sun. Look at Betelgeuse, and that's why you can see it at such a huge distance. Have it Rigel. Rigel is a blue supergiant. Once again, 860 light years. You'd never see a main sequence star that far away. Here's in the winter sky, Antares. It's a red supergiant in Scorpius. Once again, look, 550 light years away. You're seeing it so far away. You'd never see a main sequence that far away. Let's see, once again, there's Antares there. You can see why you're seeing it so brightly, clearly at long distances. Let's go over here to the pointers and the Southern Cross. So first of all, with the pointers, Rigel Centaurus, or better known as Alpha Centauri, is a 3-star system. Its main star is a close, because Alpha Centauri, everyone says, what's the closest star? Everyone says Alpha Centauri, 4.4 light years away. Absolutely. So it's a hot G-class main sequence, the same as our Sun. That's the main star out of the 3 stars. And the reason you might say, it's a main sequence star, because it's close. That's why we are seeing it. Hadar is interesting. That's a 3-star system. You've got some B main sequence stars, 3 of them there. And what did I tell you earlier? These things are rare. So have a double take at Hadar next time. That's the pointer closest to the cross. And say to someone, hey, there are 3 really rare B main sequence stars up there. And because of that, because they are brighter, that's why you can see it at a bigger distance. But there's not too many of those around. They're thin off the ground. The 4 main sort of stars that make up the Southern Cross, they are all, once again, some of them, 2 of them are singular, 2 of them are double star systems, but in each star system on its own, they are all giants. I won't go through all the details of those. All the main stars in each of those ones are forms of giant stars in that last 10% of their life. Just briefly mentioning here that stars, as I mentioned, come in clusters from these large molecular cloud, open clusters, groups of young stars, loosely gravitationally bound. So they're hanging out together, but over a few million years as they go around the galaxies, they'll just quietly wander on their way. Our sun was just on its own, but that was once part of a loosely bound collection of stars in an open cluster. You get globular clusters, which are older stars, densely packed together again. Let's not talk too much about them. They're still unwinding the pattern of, I'm going to give a talk hopefully next month about the current, what they think sort of behind globular clusters. Looking north, we see a famous open cluster. What could that be? The reason I thought I'd mention it is Matariki. Everyone says, Matariki, what's that about? Matariki is an open star cluster. It's a large molecular cloud that's condensed, formed a cluster of stars. The big ones have all blown off, and you're just with a cluster of medium stars there. And once again, it's in Taurus. There's Aldebaran. So that's why get up at 5 in the morning on a midwinter's morning. I've got better things to do, like sleep personally, and sit on the horizon. Grab a glass of wine on a midsummer's evening and enjoy, and sit back in a chair and enjoy it that way. That's me anyway. I like my comforts. Okay, that's Matariki there. The 7 sisters. Also, there's 9 big stars, but there's quite a few stars in with it. It's also known with various cultures. Of course, the Maoris. Matariki had it as for their marking their new year and so on. It's always known as Pleiades. Subaru, who's got a Subaru car? Look at the badge, it's got the 7 sisters on it. So it's a cultural significance to a lot of cultures. Okay, so what did we learn about 2,500 large stars? We see roughly, on a good clear night with average eyes, roughly 2,500 stars. Large, late-stage giants and close, moderately bright midlife stars are the main ones that we see. Stars form in clusters, and Matariki is an open star cluster. Okay, so 3 sticky messages. The first one, so when you go home and they say, what did you learn? And you've asked me about how many galaxies, how many planets, and how many stars. I should have changed it to 2,500. I didn't change it this afternoon. But the bottom line is mnemonic. We see 4 galaxies, 5 planets, and 2,500 stars. Easy mnemonic, GPS. 4 galaxies, 5 planets, and 2,500 stars. You just remember it like that, and you won't go too far wrong. So when you walk in the door tonight, guess what? So 4 galaxies, 5 planets, and 2,500 stars. I gave that on a Thursday, a talk, and about a couple of days later, I saw about 3 people at the talk, and they all came up to me. 4 galaxies, 5 planets, and 2,500 stars. And you remember it by GPS. There are a bunch of sailors, the yacht club, and I knew they'd know the GPS. I think everyone knows. So that's my little mnemonic that planets wander in the ecliptic plane and are bright and don't twinkle. So there's 4 key points that makes you realise we're dealing with a planet here, not a star. Where is it? How is it moving? How bright is it? And is it twinkling or flickering? And greater than 60% of the stars that we do look up and see are just large, late-stage giant-type stars. They're not your run-of-the-mill stars. They're in the later stage, but they're blowing up, swollen up, a lot brighter, and you can see them for further distances. Here's your homework. As I mentioned earlier on, look towards the east. You'll see Jupiter just above the horizon. So this is 30th July, 8:30 p.m. So, of course, we're in a little bit of August now, so it'll be just a little bit later on. But there's Jupiter and there's Saturn. Jupiter's the brighter one. They're all brighter than the stars around them. They're not twinkling. They're in that nice ecliptic plane. And Saturn is slightly dimmer than Jupiter, and it's got that yellow hue. Get out your binoculars or a telescope and enjoy them. So that's what your homework for is tomorrow or the next clear sky. Go out and do that and enjoy them. And point out to someone, I know they're planets, and I know which planets they are, and I'll tell you why. You may not be allowed back inside again, but anyway. So I think that's about it. So thank you very much for your attention. I hope you've enjoyed the night sky. What are we looking at? Thank you. Any questions? We had quite a few during the talk too, so I think we're all good there. Yes.
Constellation, other than the standard ones, I struggle to see the patterns and everything, especially on a very bright night where there's so many stars. How do I train my eyes?
They can be. The best thing you do is get a book and then look up constellation by constellation and try and match them up. They are a little bit out there, some of the stick figures. I don't know what they were doing around that campfire those nights, many nights ago, when a lot of those guys were coming up with those creatures. Things that have moved a little bit. I said the stars don't move in the background. There's a little bit of detail to mention there. There has been some movement around of them. But yes, also they just did, because we're upside down, we got light pollution, so they were seeing more stars mixed in there as well. But yeah, you're not alone. Some of them are obvious and some of them are not so obvious. And just know the main ones or the ones that you need to know. And I often say to people with your first telescope, don't get a computerized one. Get something like a Dobsonian. So you have to learn the night sky and star hop and stuff. And it's only with practice and stuff. But you're quite right. There's some, I struggle with how did they get that out of that? Yeah, so you're not alone.
The practical astronomy session next month, we'll look at the spring sky, so I'll take some of the constellations.
Yep, there we go.
Next month, yeah.
Yep.
And wine helps as well.
Yeah. Anyone needs a handout? There's more here. Otherwise, we're all good. So, yeah.
One question I would be on the scope. With irregular galaxies, presumably
Yes.
don't have centrifugal gravity. Does that mean planets wouldn't follow an ecliptic?
When you say they don't have centrifugal gravity?
How does gravity work in an irregular galaxy?
Okay.
And would planets in an irregular galaxy still follow an elliptical?
Yeah, okay, so you've got planets and stars. These still irregular galaxies still can have billions of stars in them, and they all got their own little solar systems doing their own little thing. But the galaxy spiral, let's go back. Early in the universe, when it was crowded and dense and the first galaxies were forming, they were probably all irregular, sort of crazy-looking galaxies. They started slowly merging together because the universe was dense, small, and with gravity and so on. They started merging. And you put that through the computer simulations and you start getting spiral structures start forming. So all galaxies start. So these are just smaller galaxies, that irregular ones today, that just haven't been matched up with, had enough collisions. They're just smaller galaxies. If you get two spiral galaxies to collide together, you'll get an elliptical galaxy, your football-shaped one. So your irregular galaxy, it obeys all the normal laws and stuff like that. It's just small enough, and it just hasn't connected in with another big galaxy yet to get swallowed up and merged and be part of a structure. So we live in a spiral galaxy because that's had time to have multiple irregular galaxies to collide and time for a nice spiral structure to develop. Yeah, so it's all about galactic. A couple of years ago, we're probably coming up, we should do that next year perhaps. There's a series of talks we do on galaxies and how galaxies form and their structures. So everything, the laws of physics, the laws of gravity, everything's still the same in that irregular galaxy, but it's just that it hasn't had time to merge. And that's what those Magellanic Clouds are all about. They're starting to merge. In a few million or billion years' time, they will slowly become part of the Milky Way. And then, of course, then we'll merge with Andromeda and become an elliptical galaxy. Yep. Does that sort of answer your question? Yeah.
That's the reason why the large and small Magellan clouds are irregular. They're sort of distorted.
Yeah, they're distorted, and they're actually getting pulled to pieces. We're actually our gravity is pulling at them, and they create streams. Go and have a look Google things like the antennae galaxies, and so we get two galaxies dancing together, and they're all ripping into each other and forming streams and bridges of stars. So we're already ripping into those two galaxies already, with the gravity just pulling them to shreds.
60% of those supergiants, why doesn't the night sky look red? Are they all red? Or when
Good question. We don't glow at night because it's just, the pinpoints, they're only pinpoints of light, they're so far away, but we can make out their colours.
So we see Antares and Arcturus, we see the red ones.
Yeah.
Is that because they're the closest?
Yes, they're the biggest and brightest ones that are there.
But the further away those red ones get, they don't
I think you'd be, yeah, I'm sure with a telescope, or without, which I focus on today, with the unaided eye, yeah, the dimmer something is, the harder it is to actually say what colour it is. But 62% of them, yeah, are red giants or supergiants. Yep. So it's, yeah, just an interesting concept. You think, well, stars spend 90% of their lives as main sequence stars, therefore 90% of the stars I look at will be main sequence stars. There's nothing wrong with that logic, but the catch is those big ones are very, very rare and they come and go very quick. They have really short lifetimes, and the ones that make up 90%, the red dwarfs, that are almost 90% of, they're just too dim to see with our unaided eye. Yep, so it just skewers all the statistics. With those main sequence ones are only 38% of what we see.
A lot of old stars, but
Yep, yeah, the Elton Johns of the world, the aging rock stars, yeah, yeah.
You've got to remember that because they're very large stars, they're not all that ancient. Like the sun would be much older than Antares or Betelgeuse because those are high mass stars that don't look like.
That table that I put up, you know, like the OB stars only hang around for 4 million years. Yeah, yep, correct. Otherwise, are we all good? Drive home safely and we'll see you next month. Thank you, good.
Can you share the slides, or is it available, or is it yours?
Yeah, no, you're welcome.